Last time we introduced Bloch sphere, I remind you that a Bloch sphere actually mapped the qubit state to our real 3D space, right? So always remember what you are seeing here does not exist in our real 3D space. It's just like you look at a map on the table, that is not the world is not on your table. We're just mapping the world's space to the 2D surface of your table. Right? Make sense? And we mentioned that for a general state, let me just recall. A general state psi equals to alpha 0 plus beta 1. We finally make it to have 2 degrees of freedom, right? And we were able to map to the Bloch sphere. Do you remember the equation? Cosine theta divided by 2 e to the power negative I phi divided by 2, 0 plus sine theta divided by 2 e to the power I phi divided by 2, 1, right? The two parameters are 0 and phi. And you find that it is just equal to the polar angle of this sphere and also the azimuthal angle of the sphere. So that is a very nice mapping. And every point in the 1 qubit hyperspace, the complex 2D complex vector space can be mapped to this sphere. Okay? Except that each point on this sphere actually corresponds to many infinitely number of states, but their phase are differ by a constant. Okay. Now I actually need to also point out that in some textbook, so this one, let me continue to write in this way. I can also say this equals to e to the power negative I phi divided by 2 cosine theta divided by 2 0 plus sine theta divided by 2 e to the power I phi. Is this correct? Yeah, I just take out a global phase, right? And that's why it's also very common, right? Maybe actually more common than what I'm using here. In some textbook, or literature, right? They only represents a general state as cosine theta divided by 2 0 plus sine theta divided by 2 e to the power I phi 1. Okay? Which doesn't matter because the global phase is the same. That's why I represent in this way is the same as this. Because you go to the same spot on the Bloch sphere. You are on the same spot. Because each spot can represent the same, all the states differ by one global phase. Is that okay? So when you see this, don't get surprised. Say why it's different, right? This one has E I phi and nothing here, and mine has negative I phi divided by 2 and E I phi divided by 2. Okay, any questions? If no, this is just a review. And then now I want to ask you, right? What is the expectation, right? The expectation of a vector on the Bloch sphere for a certain matrix. Okay, so let me recall, right? Again, this is recall. What is expectation value? Expectation value is just what? Just like mean. Right, correct. For example, if I have a dice, sorry. What are the possible outcome? 1, 2, 3, 4, 5, 6. Correct? So what are the expectation value when you toss a die? Thank you. It's 3.5, right? So expectation value is just the average. It doesn't need to be one of the possible outcome. That's 3.5, right? Very, very simple. I just want to remind you. So now, what is the expectation value of sigma c for psi? Basically, is that the question is that you try to measure sigma c, right, which is actually correspond to the spin in z direction. What is the expectation value? So, do you still remember we talked about the Hermitian matrix? And at that time, we say that every Hermitian matrix has a real eigenvalue, and that eigenvalue corresponds to the possible measurement outcome. I skip one thing. The Hermitian matrix first corresponds to an observable. Observable means that when you do an experiment, you do a measurement, you may get something, just like the dice. The dice is like I do an experiment and try to observe what I get. I may get 1, I may get 2, I may get 3, 4, 5, 6. And let's only talk about a special case. Let's say the magnetic field is in the z direction. So here we don't have physics here at all, right? Now I mentioned it, and you just agree with me. Up to now, we did not discuss anything regarding to physics. We only talk about linear algebra, right? So we say in physics, if you have a magnetic field in the z direction, then the spin can be either spin up or spin down for an electron. The reason is that they have different energy under an external magnetic field. And this one, you trust me also, okay? And sigma z, I think we discussed earlier, although only briefly when we talk about the Hermitian operator. Remember, I say the spectral value, and I showed I used the spin measurement as an example. So the spin value can be up and down, so it can be +1 or -1. And turn out sigma z is the matrix corresponds to this measurement. Okay? It corresponds to this measurement because it happened that its values, its eigenvalues, are the possible outcome of the experiment. And it also meets the physics of this process. So maybe you forgot, but what is sigma c? Do you remember? 1, 0, -1. Right, so its eigenvalue is +1 or -1. It's just like spin up, spin down. Okay? So what is the expectation value of sigma c? Means that if I try to measure the value, try to measure its spin up and spin down for a given psi. So you say I have a state which is psi. And what is when I try to measure it, it will collapse to either 0 or 1. What is the FH value? You see what I mean? Let's say it has half probability goes to up, and half of the chance go to down. Then the expectation value is what? 0, right? Because you have half 1 and half -1. And actually, we discussed this in assignment 1 also, right? So intuitively, right? Just a common sense, we can say of course, is equal to the probability of measuring 0 times 1 plus the probability of measuring 1 times -1. Correct? Now, if I give you this state, what is the probability of getting 0? How about this state? What is the probability of getting 0? Alpha's magnitude square, right? Good. And what is the probability of getting 1? Beta magnitude square, right? Now you come to here, this is a complex number, so what is the magnitude of this guy? We just cosine theta divided by 2 because this is e to the power negative I phi divided by 2. You can also go through the math. You will find that this will got cancelled because remember what is the magnitude? Is the number times its complex conjugate, right? So in that case, you will then get it's not important. But I still write it down so that it's equal to cosine theta divided by 2 e to the power negative I phi divided by 2, the whole thing squared, times 1 minus cosine, no, minus sine theta divided by 2 e to the power I phi divided by 2 squared. Is this okay? Make sense? Why I have a minus here, not plus? Yeah, thank you. It's as simple as this. Yeah, just in case you miss it, right? I hope that you don't think that there's a something special just because the eigenvalue is -1, right? Okay, so what is this? I don't know either. It's just an identity, right? So this is equals to cosine square theta divided by 2 minus sine square theta divided by 2. Check the identity, trigonometry identity. It is equal to cosine theta. Okay? Now look at this. What is cosine? What I'm talking about is this is the point. This is the state that I have on the Bloch sphere. And I'm asking what is the average value when I try to measure sigma c that I will get. And sigma c's eigenvalue represents spin up and spin down. And turn out it's cosine theta. What is cosine theta here? If you look at this carefully, this is cosine theta. Because this is a unit sphere, so this length is 1. And this is theta, so this is cosine theta. Do you see that? This length divided by 1 will be equal to cosine theta. Do you see this triangle? This, and this? This is a right angle triangle. I project vertically into the z-axis, and the length is cosine theta. See that? So this is just equal to the projection on the z-axis. Now this is another reason to use Bloch sphere. Although this is not a space really in our 3D space, but if we accept that we embed it in our 3D space, we can just think about the projection. But again, remember, we are not really doing anything on our 3D space. Just like 0 plus 1 is not equal to nothing. Okay, it's a superposition. But I can say that I can use this to help me to understand and visualize the dynamic in the future. Because now I can see that its expectation value is just this point project to the axis, which makes sense classically also. Okay? That is one thing, right? Any questions? Now, of course, now we don't want to go through this troublesome, right? We should have a better equation. And we just use what we know before. We use method 2. The way we can do is just put psi, sigma c, psi. Right? I can do it in this way. And then the rest is just a practice of what I could have put this in midterm 1 before you have learned all this, right? I just asked you to calculate. So let's calculate. What is the bra of psi? Is cosine theta divided by 2 e to the power what? Thank you. Positive I5 divided by 2 because it's the complex conjugate, right? I'm talking about the bra. And this is sine theta divided by 2 e to the power this time is negative I5 divided by 2. The whole thing is going to multiply 0, 1, 0, 0, negative 1, and then to the cat. And the cat is cosine theta divided by 2, e to the power negative I5 divided by 2, and sine theta divided by 2, e to the power I5 divided by 2. First of all, are you okay with what I'm writing? I know it's messy, but if you understand, it should not be messy. Do you understand why they are writing as they are written as row vector, matrix, and column vector in this multiplication? You should be very familiar with this because psi cat is just cosine. Although we did not write it, right? But always, let me just remind you in case you forgot. This is what? This is just a column vector. Cosine theta divided by 2 e to the power I5 divided by 2. And then sine theta divided by 2 e to the power I5 divided by 2. Right? As we have always been emphasizing since the beginning, this refers to how much 0 we have, this refers to how much 1 we have. And that's why we have this column. Right? This is alpha, this is beta, so it's alpha, beta. So alpha, beta, and z, and this one, transpose and complex conjugate. Okay, so you go through the math. I won't do that. You look at this. This is like 0 times 1 times this plus 0 times this. This is 0 times this, negative 1 times this. So basically, you still keep this term except you have a negative here. Right? This is gone, and then you have negative here. Then this term times this plus this term times this, which is negative. So again, you get the same thing, cosine squared theta divided by 2 minus sine squared theta divided by 2. And this gives you cosine theta. And of course, you should get the same result. This is just more mechanical, right? You plug in. And here is like more intuitive, classically, how you find the expectation value. Right, so in this slide, we probably will guess the expectation value of a certain Pauli vector is the projection of the state onto that axis. Any questions? Oh, okay. Let's continue. Now, my question is, what is the expectation for sigma x? Okay, it's just a practice. It will be psi, sigma x, psi, right? So from now on, if you find the expectation value, means the mean value of the matrix, you will do this operation. So we just said earlier, this equal to bra, which is cosine theta divided by 2 e to the power negative I5 divided by 2, and then sine theta divided by 2 e to the power I5 divided by 2. And what is x? I said something wrong, right? Here. What is wrong here? Thank you. Should be positive I phi. This should be negative, right? Because I need to apply the complex conjugate. Yes, this is negative for cosine and positive for sine, but I need to apply complex conjugate when I put it into Bloch. So this becomes positive and negative. Positive and negative. Okay. So what is the form of sigma x? 0, 1, 1, 0. It is a NOT gate, right? And then we put this here, cosine theta. This time I don't need to apply divided by 2. Don't need to apply a complex conjugate. And then I have sine theta divided by 2 e to the power I phi divided by 2. Okay, so let's do some operations, right? So I will keep the first term as it is, cosine theta divided by 2 e to the power I phi divided by 2. The row vector, I don't change it yet. What happened when we apply the matrix to the column vector? It's a NOT gate, right? You can think in this way. Or just do the matrix multiplication. What does a NOT gate do? Switch the alpha and beta. Yeah. So same here. 0 times this plus 1 times this will be the top now. And 1 times this, 0 times this, plus 0 times this, then this one will go to the bottom, right? So this is equals to just NOT gate sine theta divided by 2 e to the power I phi divided by 2. Cosine theta divided by 2 e to the power negative I phi divided by 2. Okay. And then the rest is just a row times column vector multiplication. Everyone okay with this so far? Okay, so row times column is what? First term cosine theta divided by 2 e to the power I phi divided by 2. Right? Some of you already see the answer, but I do it step by step. Times sine theta divided by 2 e to the power I phi divided by 2. Plus, right? This is the, I don't know what happened to the pen. Plus, right? This is cosine times sine. Now it's sine times cosine, right? So this is plus sine theta divided by 2 e to the power negative I phi divided by 2 cosine theta divided by 2 e to the power negative I phi divided by 2, right? So you see I have cosine theta divided by 2, sine theta divided by 2, sine theta divided by 2, cosine divided by 2. So they are the common term. I can factorize them, right? So that's why I get cosine theta divided by 2 sine theta divided by 2. And inside the e to the power I phi divided by 2 becomes e to the power I phi. And then e to the power negative I phi divided by 2 becomes e to the power negative I phi, right? Because I have 2 of them, right? Multiply, then you add the index together. What is this? Maybe you forgot, right? But actually not, because I have I. So good point. Yes, it almost hypothesize, but because that's I, right? So we just expand it, just recall. E to the power I phi is what? Cosine phi plus I sine phi, right? And e to the power negative I phi is just cosine phi minus I sine phi. So the whole thing gives me 2 cosine phi. Okay? So this is 2 cosine theta divided by 2 sine theta divided by 2 cosine phi. But what is 2 cosine theta divided by 2 sine theta divided by 2? Anyone remember? Huh? Sine theta. Very good. Just remember this. Sine 2 theta equal to 2 sine theta cosine theta, okay? And everything divided by 2. Now, I get sine theta cosine phi. Now, if you remember the spherical coordinates, you probably know what it means now. I have a state here, right? Which is theta. So it is phi. And if I project down to the equatorial plane, this is sine theta. The length is sine theta because it's a right angle, right? This one is sine theta. Do you see that? Right? Because it makes sense, right? Because this is a right angle triangle. When I project to the z-axis, it is cosine theta, as what we just said. Then the other one must be sine theta, right? And just go through the angle. This is theta. This one is theta. So this is a right angle. Remember, this is a right angle. So this one divided by this must be sine theta. And this is a unit length. Can you see that? Any questions? Sine theta, okay? Yeah, this length is sine theta. But how about I further project this one to this axis? Project this one to this axis is a right angle triangle. And the angle there is phi, right? So this is cosine phi. So the value that you project to x-axis is equals to the length, which is 1, times sine theta, and then times cosine theta. Right, so again, the expectation value turned out to its projection on the x-axis, or its x component. We should actually also say that equals to the x components of, now I call it phi vector, right? This vector is not talking about the qubit vector. I'm really talking about the vector in this Bloch sphere we embed in our real 3D system. Right, the real vector, right? You really see a vector here in our 3D system, right? So it's the x component of this psi vector, psi, right, vector. Not the cat that represents the 2D complex plane, but I'm really talking about the vector you see now in the 3D space. Right, because if you embed, you have this sphere, every point, yes, they correspond to a state in the 2D complex plane. But since I embed in 3D, it is also a 3D vector. But we are not using this 3D vector for any quantum computing computation. But this 3D vector corresponds to the state in the 2D complex plane, complex hyperspace. Right? So the component of this vector is just the expectation value of sigma x. Make sense? Yeah.
So I understand the sine theta is the projection onto the y plane.
Yes.
Should the cosine of phi by itself be the component in the x direction?
Yeah, cosine. Okay, yeah, but you agree cosine should be the projection of this line to here, right? Yeah, but the length of this line is not 1, it is sine theta.
Okay.
That's why your sine theta, cosine phi will give you the projection on it. Good. Any other questions? I mean, it's not too difficult. However, there are lots of things you need to review and a lot of confusion. And it is good. It's just like a review, right? If you definitely should know how to do all this computation now, right? Except I don't require you to memorize the trigonometry identities. Other than that, maybe this just as simple as before midterm 1. But now you should be very familiar with all this operation, not scared, right? And you understand what is theta, what is phi in this context. Okay. Let's continue. How about sigma y? Okay. So what is the expectation value of sigma y for any vector? Now, because of writing cosine and sine takes a lot of time and space, so now I use R and phi, alpha and beta first, okay? So this equals to alpha star beta star. What is the matrix for sigma y? 0 minus I 0. And again, I told you before, someone suggested to memorize this. Is up to you. Negative I, negative looks smaller, right? So light thing, smaller thing will float to the top. And that's how I memorize this negative one. But you can have your own method. So then I won't mess it. Alpha, beta. Okay, so we can have done that for sigma x, but now we do it. Okay, so what is this? This is alpha star, beta star. And I try to multiply the matrix and the column vector first. What do I get? What is the top element? Negative I beta. And the bottom is I alpha, right? 0 times alpha plus negative I times beta give me negative I beta. I times alpha plus 0 times beta give me I alpha. Then I continue to do the multiplication. I get negative I alpha star beta plus I alpha beta star. Right? I just multiply this with this plus this with this. Right? Very simple, right? And now I'm going to put their value. So this equals to negative I times what is alpha star? Cosine theta divided by 2 e to the power I phi divided by 2, right? It was e to the power negative I phi divided by 2, but because I have star, so it becomes e to the power I phi. And beta is sine theta divided by 2 e to the power I phi divided by 2, because it's beta, not beta star. Okay? And then continue I, and then alpha is cosine theta divided by 2 e to the power negative I phi divided by 2. And then beta, this time it has star, so e to the power negative I phi divided by 2. Okay? So with this, actually, it's pretty similar to sigma x. So I'm going to take out again, maybe I will take out I, maybe negative I. How about take out negative I? Cosine theta divided by 2 sine theta divided by 2. So this is what I've done. I took out negative I, cosine theta divided by 2 sine theta divided by 2. The first term is e to the power I phi, right? Because I have e to the power I phi divided by 2 squared. Okay? And this term, I take out negative I also, so this need to be negative. And then the next one, you go e to the power negative I phi divided by 2. Make sense? No 2. Is that okay? Right? So what I've been doing is I take out negative I because this is I, so this becomes negative. Cosine theta divided by 2 sine theta divided by 2 is here, so I have e to the power negative I phi divided by 2 squared, so I have negative e to the power negative I phi. So what is this? If you forgot again, just expand it. Cosine phi plus I sine phi minus the whole thing. Cosine phi. It was minus I sine phi, but it becomes I sine phi. Right? So this is equal to 2I sine phi. So if that is the case, 2I times I is what? Negative I is what? What is I times negative I? 1, thank you. So this, just like what we had earlier, is cosine theta divided by 2 sine theta divided by 2. And then you have sine phi. And use the same identity, you get sine theta sine phi. Which makes sense, because now it turned out that this is the projection on this y-axis. Because when you project the equatorial plane, it still use sine theta, same as sigma x case, right? But now you want to project to this axis instead of cosine phi, this time is sine phi. Right? So all this expected, this is the y component of this vector, right? So this is x, this is z, this is x, and this is y. Right? This is z, y, x. Any questions? So now we see that something pretty interesting. So when we embed the 2D space into our 3D space, although they don't belong to the same space, but we can start relate some of the 3D geometry to the state, right? Including each state is on the Bloch sphere surface, but at the same time, I can also have the corresponding 3D vector. Again, this 3D vector has nothing to do with the 2D compressed plane, right? Because the 2D is compressing, the vector is just a different space. The spin of the electron, the transmon qubit 0, 1 state or whatever. But it does correspond to a 3D vector in our real 3D space, which is real 3D. And the components of this real 3D vector turn out in this 3D space, turn out to be the expectation value of the 2D compressed planes on the 3 Pauli matrices. Right, so there's I don't know if this is an accident or there's a theory to prove that they must have this correspondence or some deeper meaning. I don't know. But at least you see this is pretty interesting, right? The expectation value of measuring the spin in the z direction of this spin of this electron turn out to be the z components of the corresponding 3D vector on the Bloch sphere. Okay, and from here we also can see that we already know that sigma z corresponds in the spin magnetic field case is that it corresponds to have a magnetic field in the z direction. Or it corresponds to like trying to measure the spin in z direction, spin up or spin down. Sigma x corresponds, you try to measure the spin in the plus or minus direction. Spin sigma y corresponds to this direction, right? So it corresponds to the 3D space in this way. So now there's another relationship, because in reality, if you set a magnetic field in the z direction in a real 3D space, that is the corresponding matrix is sigma z for the space that we cannot see. You need to think about what I'm talking about, but no, don't get confused, but it has this relationship. So naturally, you may ask, what if I try to measure the spin in an arbitrary direction, right? Measure the spin along the z direction, I use the expectation value of sigma z. And measuring the spin along the x direction, that corresponds to sigma x. Measure the magnetic field along the y direction in our 3D space corresponds to sigma y. in the, in the 2D compressed plane, right? They have this correspondence. Then why I need to really limit myself to x, y, z? What if it's in an arbitrary direction, n? Exactly, so very good guess. Then he expects that then the corresponding matrix must be the projection along that n vector. Okay, so let's take a look at this case. What's Bloch vector? What I'm trying to say here. Yeah, yes, Bloch vector. And now I know what I'm going to say. So that is what I'm trying to say. I want to introduce this Bloch vector. This one, yeah, is a state, but this one itself this is not good. This one here is also a vector. Okay, R. And this is called the Bloch vector. And what is this vector? Its x component is cosine phi psi, psi theta. Y component is psi phi psi theta. Z component is cosine phi. So I'm wrong, right? What did I say wrong? Cosine psi theta. Yeah, psi theta. That's correct. Here it almost has nothing to do with quantum computing, right? If anyone who has just took a class on spherical geometry, then they come in, they see this. Yeah, this is the vector pointing in this direction. This one corresponds to, right, corresponds to the state psi in the 2D compressed plane, right? We have this correspondence, and this is the Bloch vector. In this class, Bloch vector always reside on the surface of the Bloch sphere. I don't know which class we teach. Actually, 274, we will talk about that, right? When we go to density matrix or whatever. But when you have the coherence, you don't have a pure vector, you have a mixed state, then you will start, the Bloch vector will start shrink. And when you shrink to zero, this is a pure classical state, right? But we don't talk about this for now. Now we just say that this is a pure state, so it is on top of this Bloch sphere. It has a unit length of 1. Okay, and this is Bloch vector. Okay. So and then what do I want to say? Okay, and of course, based on this, right? This is also equal to what? This is also equals to the expectation of sigma x, x hat, plus the expectation of sigma y. Maybe let me just write down everything so you can appreciate the relationship. This also is equal to psi sigma x psi x hat plus psi sigma y psi y hat plus psi sigma z c hat. Do you see that? Again, it's a Bloch vector in our real 3D space. Fine, this is not difficult, right? But I want to tell you that this Bloch vector, of course, equal to cosine, and this, I need to remind you what is the meaning of this matrix, right? It means it has this amount of x hat, this amount of y hat, this amount of z hat. This is completely a 3D vector in our space. And how do you find that component? It turned out to be the expectation value of sigma x, sigma y, sigma z of the corresponding state. Okay. Right, so it's confusing, but think in this way gradually, okay? And that's why I don't want to talk about Bloch vector at the very beginning, Bloch sphere at the very beginning. Okay? Now, so with this, let's start thinking about what is the expectation value of a linear combination of a Pauli matrix. Okay? So, right, what's the expectation? So first of all, we introduce, and we actually discussed this before already, right? Pauli vector. We discussed this before, but maybe you forgot. Is Pauli vector turn out to be sigma x, sigma y, sigma z. You might say, wow, what is this? This is a column vector, right? But what is sigma x, sigma y, sigma z? They are matrix. Okay, so remember when we say vector, we go back to what we discussed before. What is a vector space? It's not limited to the vector we know with this column element. Its elements can be anything, as long as it fulfills the definition of vector space. For example, it has a field, right? It has a complex, it has some number that you can do for multiplication. You have this distribution law. You have an identity vector or zero vector. I forgot all the definition. So this one as by itself can be the elements of the vector. What is the meaning of this, right? It's like this, very confusing. 0, 1, 1, 0, 0, negative I, 0, 1, 0, 0, negative 1. Okay? But when we say vector, do you still remember? You need to tell me the basis, right? You have coefficient and the basis, right? So what is the first basis of this? I told you, but maybe you forgot. If you forgot, that's fine. X hat, Y hat, Z hat. So again, this is not a vector in our real 3D space, right? But it does use our real 3D space as the basis. Okay? Which is just equal to sigma x, x hat, plus sigma y, y hat, plus sigma z, z hat. And this is the so-called Pauli vector. And we discussed this before. It can be confusing, but you need to swallow it, right? You need to accept it, because based on the definition of a vector space, this is correct. It fulfills all the requirements. Okay, so this is a vector. Okay, and then we define another unit vector. Which is n. This is a real 3D space vector that we can see. Nx, ny, nz, which means it is nx, x hat, plus ny, y hat, plus nz, z hat. This one is okay, right? This is easy. But what is the meaning of unit vector? What is the meaning of unit? Length equal to 1. How do you find the length of this vector? Yes. Right? This is just a regular unit vector that we learn, right? Okay. So a general combination of Pauli vector Pauli matrices are sigma dot n, the inner product between sigma and n. And what is the inner product? You know already, right? Because the bases are x hat, y hat, z hat. So the inner product is going to be the multiplication of the corresponding component. if you forgot. Again, how do you do inner product? Bra times cat. So this is going to be, to avoid troubles, let me do it as, I don't want to go too deep. Okay. So this is going to be sigma x, sigma y, sigma, no. Nx, Nx, N, Ny, Nc times sigma x, sigma y, sigma z. Right? Are you okay with what I'm writing here? It's just a regular 3D vector, except this guy is a matrix, right? Inside. So that's it. So this is equal to nx sigma x plus ny sigma y plus nz sigma c. And then you just go to the form. This is 0, 1, 1, 0 plus ny 0, negative I 0 plus nz 1, 0, 0, negative 1. Right? You go through the math. This is just equal to what? 1 nx minus I and y. X plus I and y. Negative 1. That is a matrix corresponds to unit vector n. Right? For example, sigma z correspond to unit vector pointing up. Sigma y correspond to the unit vector pointing in the x direction. Sigma y correspond to the unit vector pointing to the y direction. And this n dot sigma correspond to the unit vector pointing to the n direction. This is just a general case. Yeah. Yeah, what do you think? Because, again, my mistake. Typo, sorry, thank you very much. Should be NC and negative NC. Thanks for catching that. Now, so this is what we have, right? Now, then what is the expectation value now? I should have one more slide, but actually don't have enough space. Keep writing too much. So what is the expectation of sigma of n dot sigma? Oh, this one. Well, you are welcome to do the matrix multiplication, right? But you can also remember this is just linear. This is just equal to nx sigma x plus ny sigma y plus nz sigma z. And then I don't have space. Right, the whole thing, right? Which is equal to, because it's linear, right? I can take this out equal to nx times the fh of sigma x plus ny times the fh of sigma y plus nc times the fh of sigma c. Is that okay? I'm jumping a little bit. Right? I already show you this is equal to this, right? So the expectation value of this matrix is just equal to expectation value of each of these terms. And x, nx, ny, nc are just numbers, so I put it outside. So that's it, right? But what is sigma x, sigma y, sigma c average expectation value? We learned that already. This just equal to cosine theta sine phi plus ny sine theta sine phi plus nc cosine theta, right? I just plug in what I learned, what we derived earlier. Is that okay? But this is nothing but just what? Nx, ny, nc is just the n, the unit vector. And cosine theta, sine phi, all these are just the Bloch vector. Right? So this is just conclude what you guessed earlier. The expectation value of the state for this general matrix, which correspond to the direction n, is just equal to the projection of that Bloch vector onto n. Let me write this down. Projection of psi on n. That's it, right? So if you have a state and you say, I want to measure the spin value in a particular direction on n, then it is just equal to the overlap of it. Yeah. Where I'm not doing rotation. Can you say again? This matrix.
Yes. Like very property.
This is unitary. I mean, why do I need to? I'm not doing rotation now.
You're not doing rotation. That's why I said it's off topic.
Oh yeah, I'm not doing rotation. I'm just finding the expectation value of this matrix. And it turned out to be the corresponding Bloch vector projector on n. Okay, yeah. Okay, I know this is confusing, but I mean, to be frank, if you want to learn quantum computing, maybe I did not, it's messy, I know. You can read my book or the two books, but the point is you need to appreciate every point here, feel comfortable of what I'm talking about, and then have an idea to correlate the measurement to the matrix, Hermitian matrix, have an idea about the projection, how the real 3D vector correspond to the virtual, I mean not virtual, the compressed 2D hyperspace vector that we cannot see. Right? So again, everything, so there's a relationship. That's why Bloch sphere is so useful. For example, at the end we are talking about the real vector in R, the real vector R, which correspond to the state. And n correspond, for example, to the magnetic field you try to set up or the direction of the spin you try to measure. These are real, right? But it turned out that it has some relationship to what we don't see, we cannot see. Okay, let me just finish the rest then. Okay, so now you talk about rotation, but we won't go deep here, okay? So I want to mention one important thing is how to construct the gate. So now we know that we have real 3D space, and this is just where we embed our Bloch sphere there, right? So now we can really talk about the rotation of the state in 3D, because We know it is not rotating in 3D. We know it's just rotating on Bloch sphere, but because we embed Bloch sphere in our 3D space, when we say, we definitely can say rotates about z-axis. So when we say, I have a state, I want to rotate it about the z-axis, it means that it rotates on the Bloch sphere embedded in our real 3D space. Okay? But every point on the path corresponds to a state in the 2D compressed plane that we don't know. Right? So let's use the map as an example. Right? Again, I told you that, okay, if we look at the map, we map the Earth, right, onto our desk. So let's say, I don't know how to draw the map. This is America, right? And then let's say this is Africa, right? This is South Africa, right? And this is San Francisco. And we map it to the Earth, so to the 2D plane. So here is America. So this is San Francisco, right? This is SF. This is SF. And then we have Africa here. I don't know. Okay, and then here you have, I think we need to talk about, let's say Japan, Tokyo, right? Tokyo. So Tokyo is on the other side of the Earth, you cannot see on the other side. So what we are trying to say is that, okay, when I go from SF to Tokyo, I actually need to go through this edge, which does not exist, and then come back in Pacific Ocean again, right, from SF to T. And I can say about this, I go to the left and then disappear and reappear from the right. In this process, in the real space, you are actually doing a circle on this sphere, right? Correct? Here is like this. Here is like we have a space event I cannot draw, which is 2D compressed plane. And when I say the state rotate from here to here, it has its own path in the 2D compressed plane. So when I say I'm rotating, when people tell you I'm rotating the qubit about z-axis, about y-axis, it's talking about I'm rotating the qubit on the Bloch sphere, which embed in the real 3D space. And you can see that it's rotating there, but it's not really rotating in our 3D space. But this process, we can think it as rotating in our 3D space. But in reality, in the 2D compressed plane, it is rotating in a way that we cannot see. Just like a kindergarten or a baby, right? He or she doesn't understand the mapping of this map to the real Earth. They will say, oh, so easy, I can just jump to nowhere and then appear on the right, right? But in reality, if you go to the real state on the Earth, you are actually rotating on the Earth, right? Because it's sphere, like this, okay? I hope this analogy makes sense. So now, we want to say that if you want to rotate a point from another point to another point on Bloch sphere, you can decompose it into free rotation, and that is something called the Euler rotation. Right? So we don't prove it here, but you can prove it or look at my book. But basically is that I can decompose all rotation. So here is unitary gate. So this unitary gate has three parameters: theta, lambda, and phi. This corresponds to what? You first rotate about the z-axis by lambda. Then you rotate about the y-axis by theta. Then rotate about the z-axis by phi. Then you will be equivalent to this unitary gate. So basically trying to say is every rotation on this Bloch sphere can be decomposed into free rotation about two axes. Is that okay? This is just what I want to say. Okay, you trust me, any rotation, just like now on Earth is the same, right? You go from here to, let's say, South Africa. You don't need to fly rotate in that way. You can rotate about North Pole for a certain angle and then rotate about y-axis for a certain angle. You still can go from San Francisco to South Africa. So every rotation can decompose into this three, right? And again, what is a quantum gate? Quantum gate is the rotation from on the Bloch sphere, because you go from one state to another state, right? Isn't that is a rotation on Bloch sphere? So it means the quantum gates can be decomposed into three quantum gates, which at worst case, right? So rotates about z, rotates about y, and then rotates about phi. You can also decompose into x and y, right? But this example only show you z and y. Any questions of what I'm trying to say? Yeah.
I understand the rotation, but what's the meaning of the U?
So U is a general quantum gate, unitary gates, right? Or general rotation. So for any quantum gate, you can represent in this form. And they are characterized by three parameters: theta, phi, and lambda. So once you have theta, phi, and lambda, you fix a quantum gate. We actually ignore the global phase, but let's just take this. Okay? And turn out theta, lambda, and phi correspond to this free rotation. Is that okay? So let's do an example. For example, NOT gate, right? What is a NOT gate? 0, 1, 1, 0. Okay? So it must be equal to this, the general form, right? There are certain theta, phi, lambda will give me NOT gate. So we solve equation one by one. We will equate the elements. Right? The first thing, NOT gate 0, 0. What is 0, 0? 0, right? That's the first element. It has to be equal to what? Cosine theta divided by 2. This element equal to this, correct? So what will be theta if cosine theta equal to 2? Cosine theta divided by 2 equal to 0. What will be theta? Pi, thank you. Good. Okay, then not 0, 1. What is 0, 1? 0th row, first column, what is that? 1, right? It equals to what? Thank you. Minus e to the power I lambda sine theta divided by 2, right? But what is theta? We fixed theta already, right? What is theta? Pi divided by 2, right? So, but what is sine pi divided by 2? 1. Okay, so 1 equal to negative e to the power I lambda. What will lambda be? Not easy, right? So this one, we just remind us, this is negative cosine lambda minus I sine lambda. How can I make this 1? How can I make this 1? I need cosine lambda equal to negative 1, right? And like what you said, it needs to be pi. Because sine pi equal to 0, cosine pi equal to negative 1. So negative 1 times negative 1 equal to 1. Okay, so I continue. How about not 1, 0? That is 1, right? And it's equal to e to the power I phi sine theta divided by 2. Now I already know what is what is theta divided by 2, right? What is theta, right? Which is pi. So this gives me e to the power I phi, right? So what should be the value of phi? 1 equal to e to the power I phi. What should the value be? 0, thank you. So phi equal to 0. Okay? Now, I actually fixed all parameters already, but I need to make sure the last one is correct. And, not 1 equal to 0. And let me plug in equal to e to the power I. What is lambda? Pi. What is phi? 0. Cosine pi divided by 2, right? I just use this equation. Lambda plus phi. Lambda, we already find that is pi. Phi wanted is 0. And then theta is pi. So cosine pi divided by 2 is 0. So this is 0. So this is correct. Yeah.
Can you spell out the phi really quickly? E to the I, phi is 0, e to the I 0 is 1.
Yeah. So this is 1.
Oh.
This implies phi equal to 0.
I thought I'd be, yep.
Yeah, I know what happened. Me too. Make sense? Okay, so the last line is this. Let's give the Qiskit. So, I just tell you, lambda equal to pi, phi equal to 0, theta equal to pi. Lambda equal to pi, phi equal to 0, theta equal to pi, right? Do you see that if I want to construct a NOT gate, I need to follow this. For example, look at this plus state and minus state, plus state. The first rotation is what? About z-axis by pi. So you come to here. The second rotation is about y-axis by pi. So it comes to here. And then the last rotation is 0. Don't do anything, right? Based on what we said. So is this correct? Yes. NOT gate applied to plus will still give me plus. Do you remember? NOT plus is just equal to NOT 1 over square root 2, 0 plus 1. So when you do the NOT, 0 becomes 1, 1 becomes 0, which is still equal to plus. Make sense? So this is correct. But sometimes we try to use special case and try to do shortcut, keep thinking, your NOT gate is from 0 to 1, right? And 1 will become 0, right? Let me just rotate this by pi, right? Isn't that if I rotate about y-axis by pi, 0 will become 1, 1 will become 0? That's the operation of NOT gate, right? But if you only do this for other states, you rotate by pi, then plus will become negative. And this is wrong. Right? This is not a NOT gate. So if you want to create a gate, you need to follow this procedure. So that's why you need to be careful about what the gate construction when you use Bloch sphere. Do not use a special point and then you thought that I can rotate from here to here. Then this is NOT gate. But turn out NOT gate is pretty complicated if you want to decompose it. Okay. So I will stop here. Thank you. Any questions?